done equipotential surface. Yes, first view, any doubt, anything to, any confusion? Yes. Anyone having any confusion?
Sir, I will solve the sums and I will tell you.
Huh?
Sir, I will solve the sums and if I have doubt, then I will tell you. So from next class, I will.
No, in the understanding what we have discussed,
No.
electric potential due to point charge, electric potential due to dipole, electric potential due to many charges, and potential energy. In understanding the concept of these all, anyone having any doubt? No. So we are discussing about equipotential surface. So in case of equipotential surface, what will be? If this is equipotential surface having potential V1 and another one is equipotential surface having potential V2. So due to different system of charge, different type of equipotential surface will come. So due to a point charge, it may be a sphere. So equipotential doesn't mean zero potential. Means potential is same everywhere. That is the meaning. So like we have discussed yesterday, work done in moving any charge from point A to B. If we move any charge Q from A to B on equipotential surface, work done will be 0. So work done from A to B, which is Q VA minus VB, if it is electric field by field. If it is by external agent, then VB minus VA. So it will become 0 because VA and VB both are same. Now, work done by electric field, it can be EDR integration cos theta QE, of course, not E, QE, but force is QE here. So work done by field is this one. So whatever distance we are considering, now in this case, what is happening? Neither E is 0 nor DR is 0. Since E is not 0, DR or R is also not 0. But this product is 0. When it is possible?
Theta is 90.
That means this cos theta is
90 degree.
So theta is 90 degree. So what does it mean? Electric field intensity will be perpendicular to the surface. So it shows E is perpendicular to equipotential surface. it will be pointing outward or pointing inward. That will depend on how the potential is changing, whether it is increasing or whether it is decreasing. So if V2 is less than V1, electric lines of force always move from higher potential to lower potential. So these are the properties of equipotential surface. So potential will be same everywhere. Work done in moving any charge from one point to other on the equipotential surface will be 0. Electric lines of force is perpendicular to equipotential surface. Electric lines of force will always move from higher potential to lower potential. So if the equipotential surface potential is decreasing, the electric lines of force will be from suppose left to right if it is decreasing in this way. Now, if equipotential surface is plane surface, then electric lines of force will become in this case equipotential surface is a plane surface. Okay, suppose these are the lines. This is potential V1, this is potential V2. So what is the relation? V1 is more than V2 or V2 more than V1? If electric lines of force is as shown in the figure, what will be the relation? V1 more than V2 or V2 more than V1?
V1 more than V2, sir.
V1 will be more than V2. Electric lines of force will always move from higher potential to lower potential. Okay. So in this case, this V1 will be more than V2. And this is for electric field. Then what will be this V1 minus V2? What will be V1 minus V2? So V1 minus V2 will be E into D. Yes? No, this electric field intensity is minus dV over dr. So minus dV is E dr. Is minus of V2 minus V1 is E dr. Here it is called 0. So this V1 minus V2 is E dr or R, whatever you may say. So the distance, identity uniform electric field. So dr, the distance between the two planes. So So if electric field is strong, in that case, what will be? For same potential difference, this interplanar space will be less. Or if E is more, naturally D will be less for the same difference. So for a strong electric field, the distance between two equipotential surface will be less for same potential difference. Okay. So these are the property of equipotential surface. If electric field is strong, then distance between two different equipotential surface will be less for same potential difference. What does it mean? Suppose we are saying this is the uniform electric field. Maybe uniform, maybe non-uniform, whatever it is. So suppose this is uniform electric field, and we are considering one equipotential surface here and one equipotential surface here. If this V1 is suppose 10 volt, this V2 is 5 volt. This distance is suppose 2 meter. Okay. Just assumption or whatever distance suppose G1 will be. Now, if the field is like this, during the same region, electric field is like this. Now, when one equipotential surface is here, this is V1 is 10 volt. Now, another equipotential surface for 5 volt will be at a distance more than this or less than this?
Less than this.
Less than this, not more than this, less than this. So when the field is very strong, this distance between the equipotential surface for same potential difference. For a difference of 5 volt, if here is 2 meter, here it will become much less than 2 meter because field is very strong. So this E dash is more than E, then this D2 will be less than D1. That is the case here. So if electric field is strong, in that case, distance between equipotential surface for same potential difference. When we are comparing, the potential difference constant, or for per unit potential difference, whatever you may say, for 1 volt only. So for 1 volt, whatever the distance here, here it will become less. So when E is more, dr will be less. The product of E and dr is V1 minus V2. Now, electric potential at any point due to charge metallic solid sphere, you can say, or conducting solid sphere, whatever you will say. Or spherical shell. Conducting or non-conducting, whatever it may be. Spherical shell may be conducting material, that is metal one, or it may be insulating material one, no problem. Both will have same formula. Here only we have to know the formula. Derivation is not in our syllabus. So only we have to know the formula, what will be. So as you know, in case of metallic sphere or the conducting sphere, in place of metallic, conducting may be written. So conducting sphere, conducting solid sphere, or spherical shell of any material, may be conducting material. So what is here? All the charges will be present on the surface only. If it is a conducting sphere, maybe solid also, no problem, but charge will be present on the surface only. If it is insulating material, as it is hollow, so charge is present on the surface only. Now you know this is behaving like a point charge. We have derived the electric field intensity, and we got it is behaving like a point charge. As far as the point is where we have to find the electric field intensity, that point should be outside or on the surface. Inside, what was that? What was the electric field intensity?
0.
0. So when the electric field intensity, this is suppose at E1, this point is E2, and this point is E3. So E1 was, if this distance is R, this is radius is A. So E1 was 1 by 4 pi epsilon naught Q over R squared, where Q is the charge present on this. That's what the E1. Now electric potential will be also same as if we assume a point charge at this place. So what is the electric potential? 1 by 4 pi epsilon naught Q over R. When we are considering a point charge present at the center, whatever the potential will be. So V1 is this much. Now what will be E2? So this E2 is how much? 1 by 4 pi epsilon naught Q over A square, where A is the radius of that sphere. And this potential will be also same, 1 by 4 pi epsilon naught Q over A. Now this E3 is 0. When the point P is inside the sphere, electric field intensity is 0. But potential can't be 0. Why? If we consider the individual charge, potential due to this charge positive, potential due to this charge positive, potential due to this charge positive. So net potential can't be 0. What does it mean? How is it possible then? Intensity is 0, but potential is not 0. What does it mean? Is it possible? Yes. Is it possible? Electric field is 0, but potential is not 0. It is possible means where there is no change in potential. E is dV over dr. If dV is 0, that is V is constant. So electric potential at any point within this sphere will be same as that on the surface. So inside that sphere, electric potential is constant. So this E3 will be same as E2. That is 1 by 4 pi epsilon naught Q over A. So this result we have to keep in mind. At any point within the charged spherical cell, or conducting sphere, is constant and is same as electric potential at any point on its surface.
So there it will be V3 and V2, sir.
Yes?
It will be V3 and V2.
V3, yeah, sir. V3 will be equal to V2, and that will be equal to 1 by 4 pi epsilon naught Q over A. So at any point within the charged spherical cell or conducting sphere, at any point within this, electric potential is constant. Electric potential is constant and is same as that of or electric potential at any point on the surface. So electric potential within this hollow sphere is not 0. Electric potential is there, but intensity will be 0 because electric potential is same everywhere. So dV by dr will become 0. Now, if you want to represent it graphically, what will be? Suppose this is the whole sphere. So E versus R graph we have already done. What was that? If this is A, this will be plus A, this is minus A. So it was 0 up to here, and there is sudden increase at this place, and that is inversely proportional to R square. 1 by 4 pi epsilon naught Q over R square. And here it was, this Q2 was 1 by 4 pi epsilon naught Q over A square. And here it was, E3 was 0. Now, when we plot potential graph, what will come? So, this is suppose V graph, potential one. Here it is 0. So, it is 0 plus A minus A, potential will remain constant. From here to here, everywhere it will be same. After that, it will keep on decreasing. And this graph will come like this. This graph will be steeper than that graph. So here, this potential will be 1 by 4 pi epsilon naught Q over R. And this one is V2 here. This V3 also same. So this graph slope will be that is steeper than this one. See, inversely proportional to R. That is inversely proportional to square of R. So electric potential at any point due to charge non-conducting sphere. This is not in syllabus. ISC syllabus is not there. So it is same as we have calculated electric field intensity. So if this is the charge sphere of non-conducting material. So in this case, what will be? Charge is present throughout the volume. In case of metallic sphere, charge is present only on the surface. So as far as outside is concerned, it is same. 1 by 4 pi epsilon naught Q over R. Same as that one. Here, VQ will be 1 by 4 pi epsilon naught Q over E. That will be same as metallic sphere. Only inside it will be different. So if point P is somewhere here, as we have done in that case, we will consider this sphere only. We will calculate what is the charge present or charge enclosed by this sphere, as this point P is on the surface of this sphere. So this formula will be applied, but in place of Q, this much charge will come. In place of A, this distance will come. So this charge enclosed will be how much? The total charge over 4 by 3 pi AQ into this volume. Okay, so what will you name? Okay, suppose this is the R dash. Now, what will be electric potential at P? At any point, this one within this or at P, we are interested. Okay, will be 1 by 4 pi epsilon naught Q over R dash. Because point P is on the surface of this sphere. So this one will become 1 by 4 pi epsilon naught Q R dash square over E. So this way we can find the electric potential. So if R dash is less than A, then this formula, R dash equal to A, then this one, this one, and more than that, like that, same. But it is not in our syllabus, only for competitive exam, you can consider this way. So in this chapter, only this much we have to know. Now, some numericals. Anyone having any doubt, anything? Have you solved the numericals of the book? Only 13 are present. Why so less? I don't understand. Ravel, where were you? You didn't give the second test? Ravel? No response? Sleeping or what? Where is Shreyas today? Anmol?
Sir, he is sick.
Sick. What happened?
Headache.
Sakshi was also absent. Okay, many are frequently absent. Rajnarayan came yesterday, today absent. Okay. Yes. Have you solved the problems? No.
No, sir.
I am out of station, and when what was that? I didn't read book. Okay. So, suppose you are given this is a square. Here at each place, suppose plus q, minus q, plus q and minus q charges are present. So you are asked, find the work done in moving plus q charge from B to O, and O is the point of intersection of diagonal of square ABCD when each side is A. Okay, now you are asked how much work will be done in moving this plus q charge from B to O, and the point O is the So what will you do? As you are asked to find the work done in moving plus q charge from B to A, that is this particular charge we are moving. So leaving this charge, remaining charges are the source. So we'll find what is the electric potential due to these charges at point B. What is the electric potential due to these three charges at point O? And then work done, charge into potential difference. So try to find. Yes, anyone got? Hmm? Got anyone? No.
Root 2 k square.
So we'll find the electric potential at point B due to this, and this. So 1 by 4 pi epsilon naught. Due to this, what will be? Q over A. Due to this, minus Q over A. And due to this, plus Q over distance is A root 2. These two cancel. So we are getting here KQ over A root 2. Because this charge is to be moved. So this is not the source. So electric potential due to remaining charges we have to find. Now similarly at point O, again due to this and this equal and opposite, so it will cancel. So only this is left and the distance is Q and here is A root 2 by 2. So it will be A by root 2. So electric potential at O will be root 2 KQ over A. Now what is the work done by external agent? As it is moved from B to O. So charge which is moved and we are moving this one to charge. So plus Q charge is moved. Potential at VO minus VB. Yes. So it will become root 2 K Q square over A. Yes, any confusion?
No, sir.
Okay, suppose this is given. Figure may not be given. It's like this language is very clear. So figure may not be given. Figure you have to draw yourself. Yes. Well, this much time will take. in 20 minutes this type of 5 sum will come, then what you are doing? You are guessing your answer or what? How you are doing this 5 sum in 20 minutes, by guessing or by solving? So again, this charge is to be displaced. So we'll find electric potential due to this and this at this point as well as at this point. So net electric potential at A 1 by 4 pi epsilon naught. So this is 1 over 2 plus 1 over 2. So it is 9 into 10 to the power 9 volt. Okay. What is electric potential at D? 1 by 4 pi epsilon naught. 1. So it is 18 into 10 to the power 9 volt. What is the work done? Work done from A to D will be the charge which is moved 1 coulomb into Vd minus Va. So it is this minus this. So 9 into 10 to the power 9 joule will be the work done. What will be the time? Work done by power. So 9 into 10 to the power 9 joule over 500 watt. So this much second. So it is 1.8 into 10 to the power 7 seconds. So this much time will be taken. That is more than 1 year, no? No. Yeah, more than 86400 into 365. Yeah, more than 1 year it will take. So if average power of a man is suppose 500 watt, then he will take more than 1 year to displace this 1 coulomb charge to this place. So the work is very high. It will take much time with average power we are considering. So in this way we will calculate what is the work done and or how much time it will take. Okay, suppose this is given. So in this case, you are given electric field is 50I, means it is uniform. No? XYZ is not coming with that. So 50I means electric field is uniform and its direction is along x-axis. The point is displaced, or the charge, this one is displaced from here to here via this one. So how will you solve this problem? So as electric field is uniform, then what will be? So work done from A to B. Via doesn't matter, whatever way may be. In case of conservative force, electric field, gravitational field, magnetic field, important is from which point it has started or from which point it is, at which point it is reaching. Only these 2 points are important. Via whatever they are moving, no problem. They are going through circular path or they are going through curved, means straight path or whatever it is, so it doesn't matter. Simply we are interested, okay, it has started from here, it has gone to this place, whether it is going this way, whether it is going this way, or whether it is going this way, or it is moving this way, no problem. Only it will be whatever the charge is moved and potential of VB minus VA. So as this field is uniform, so what will be? This will be Q E R negative side. And you know this intensity is dV by dr with negative sign. So this dV will be E dr with negative sign. So this is RAB, and it is displaced from A to B. Or you can think in this way. Suppose electric field intensity in this direction. The particle is displaced from here to this place. The charge is Q. So electric field will apply force in this direction. Displacement is in this direction. Work done, that is QE dot R AB. Like this is work done by electric field. Work field. By external agent, minus of this. So minus of this will be. Now how will you find this RAB? That is position vector of B minus position vector of A, displacement vector. So it will be minus QE and RAB is what? RB minus RA. So first we find RAB will be how much? 9i minus 4j plus 10k minus 2i plus 3j plus 5k. How much it will come? So 9 minus 2, that is 7i, minus 4 minus 3, 7j also, plus 10 minus 5 plus 5k. Is it correct? So it will be minus q is how much? Plus 30 microcoulomb. Electric field you have given 50i. And this one we got 7i minus 7j plus 5k. So how much will come? I dot I will remain and rest 0 only. So it will become 50 into 7, that is 350. 350 into 3. How much? 105. So 1050. Is correct. One more 0. Into 10 to the power minus 6 joule. With negative sign also. So it is minus 1.05 into 10 to the power minus 2. So work done by external agent will be negative. That means external agent will gain this much energy. If you are asked work done by field, then this is the work done by field with positive sign. Work done by field, if it is there, work done by electric field, it will become 1.05 into 10 to the power minus 2. And here negative sign will not be there. Sorry. So in case when electric field is given, then we will apply dot product of the E and R. If potential is given, then this will be the formula. Now another type question may be, if V electric potential is given by 3I minus 6J plus 2K, this is volt, this much volt. Find, oh no, the I will be very constant. 3xi 6y square j and 2z cube k. Like this is given. 3xi minus 6y square j plus 2z cube k. That much volt. find electric field intensity at point P, which I got the coordinate 1, 2, minus 3 meter. Okay. So as we know, this electric field intensity is minus dV over dr. So we'll find x, y, z components separately. So we'll find Ex. So this Ex will be minus of dV over dx. So if you differentiate this with respect to x, that means this y and z is constant. When we differentiate with respect to x, y and z is not variable. So what will come? So it will come only 3i, negative sign. Similarly, this Ey minus dV by dy. So only differentiation of this one. So how will it come?
Plus 6j.
Plus 12y.
12.
2.
2. Sir, 6 no, sir.
2 into 6.
2 is square is there, sir.
Differentiation of y. Huh?
It is y square.
Yes?
It is 6y square.
Yeah, 6y square.
Yes.
Oh, then 12.
And this one is, so Ez will be minus dV over dz. So minus 6z squared. Is it so?
Yes, sir.
So what can we write? This intensity is how much? So minus 3i plus 12yj minus 6z squared k. This is the intensity. Now we are interested to find intensity at this particular point, where value of x is 1, value of y is 2, and value of z is minus 3. So electric field intensity at point P. And this is does not depend on x. That means along x-axis, electric field intensity is uniform. Electric field intensity is varying along y and z axis only. So at this particular point, what will be? This is minus 3i plus 12 into 2j minus 6 minus 3 squared, 9. So electric field intensity at point P is minus, if you are taking common, then it will become 3i, or 3 also you can take common, no problem. Minus 3 you can take common, then it will become I plus, no not plus, minus 8. 8j plus 18k. If you are asked find the magnitude and direction, then after that as vector we will solve. If simply you are asked find electric field intensity, you can leave up to here because you are not tested here vector. So if you are leaving that also, no problem. So electric field intensity at this particular point is this much. So this electric field is varying along y and z axis, but x axis it is constant. So this way you solve the different problems.
This chapter is completed, sir.
I think so.
That earthing one.
Where is earthing?
Yeah, the question was there.
Earthing means where earthing is done, that is zero potential.
Yeah.
Suppose any point is earth, that means potential at that point is zero. That much only you have to consider. Okay, so shall we leave?
Yes, sir. Thank you, sir.
Yes, sir. Thank you, sir.
Yes, thank you.